Okay, today we're going to take a slight detour into the kinds of metrics that we get out of these kinds of simulations. We're going to focus on averages with the understanding that averages aren't the only thing, but they're the most common thing. And it turns out that there are actually two types of averages, as we've alluded to yesterday. The one that's actually most common in discrete event simulation models are actually time-varying averages. And what you've experienced in your statistics classes is what we call a tally average. The difference being that the time-varying is typically the area under the curve divided by the time, which is a different way of computing things, whereas a tally is what you're used to, where you have a sequence of numbers, you add them up and divide by the number. And as you hopefully saw yesterday, when we're dealing with values that take a certain amount of time, that amount of time that you spend in those states needs to be taken into account when you're looking at the average. In other words, think of, suppose we had some variable that was either 1 or 0, just make it simple. And let's say over a period of a year, it was 0 for 1 day, and 1 for 364 days. So the question is, what is the average value of this thing?
180.
Well, it would, yeah. In other words, would you, if you would do it in the tally way, you have two observations. You have 1 and 0, and so the tally would be 1/2. But intuitively, does that, if you spend 90% of your time as 1 and 10% of your time at 0, then saying it's just the average of the two intuitively should not make any sense. Intuitively, since you spend most of your time in, in state 1, then that fact needs to be taken into account. Question?
To the time varying average, is that essentially just like a weighted average or it weights the time?
Yeah, you can think of it that way. And as we'll see, there's a very specific way of computing it that takes all of that into account. And then it turns out that in many systems, there's an interesting relationship between certain time varying averages and certain tally averages. And that's something called Little's formula, which we will see in a moment. So again, there are two types of averages that we need to consider here. The tally is what you're used to. We have discrete observations, and the way you find the mean is by adding up and dividing by the number of observations. So that shouldn't come as a huge shock to anybody, because that's what you've been doing for quite some time. The time varying has to do when we have continuous observations, and this is actually valid in situations beyond discrete event models. In situations where we literally have continuous observations, the same principle applies. It's just that in a continuous, if a purely continuous observation where the function is some continuous function, then you would need to take the area under the curve, which involves calculus, which we're going to avoid. We can't completely avoid it, but we'll see when we have to. So in discrete event models, because the states are piecewise constant, our areas will never be more complicated than the areas of rectangles, which is just the width times the height. And here, the width is going to be the amount of time that you spend in the state, and the height is going to be the amount of the state. So let's look at a specific example from our little hand simulation model that we did yesterday. And to just summarize what the simulation model produced were these three state trajectories. And I've been using the term state trajectory, and what is that? That's simply just conceptually the value of a given state variable as it evolves over time. So the trajectory part is the time, and the state trajectory is just kind of you can think of it as the function. So for Q, we had something that looked like this. And so if we were to graph this, which we will in a couple slides, actually here, no, one slide. So this is what these three state trajectories looked like. So here for the number in the Q, remember we had that little spike, and then it stayed with 1 in the Q for a while, and then when I went down. For the number of available servers, it actually started at 1, then dipped back down to 0. It popped up to 1 briefly when it finished service, and then finally ended at a state of 1. And then if we were to graph the number in the system for the same values, it kind of looks like this, where we have this little stone thing. Now the thing is that as the simulation unfolds, it's important to not have to remember all of the data for this, because we'll typically be running many replications of simulations, sometimes literally for millions of time units, and there literally may be millions of state transitions that we need to keep track of. And so it turns out that if we want the average, what we need is the area under the curve, and to find the area under the curve, what it turns out to be the most efficient way of doing that is by keeping a running total of the area and then simply updating it every time a state changes. In other words, if we were to look at the number in the system, which is the most interesting one for the short amount we did, between the run event at time 0 and the first arrival at time 2.1, we were in state 0. And so at time of 2.1, what is the area under the curve? 0. Okay. So now the next state transition, the next event occurs here, which I believe is 3.5. So at time 3.5, how can we update the area of the curve? Well, yeah, exactly. So we were at 0 here, so that was the last running total. And so at this event, all we need to do is update by the area in this rectangle. And what is the area of that rectangle? It's the base times the height. And what is the height? The height is the old value. So we were at 1 for a while. So it's not the new value, because that would be too big. It's the old value times the amount of time that we've spent in that state. So in this case, we went from 2.1 to 3.5. So we were in that state for 3.5 minus 2.1. So that's how long we were in the state. And then the value of the state was 1. So we would get, what, 1.4? So at this time, the area is 1.4. And now, okay, so now at the next event, which was it was at 4.3. So here at time 4.3, our running area was 1.4. So how long were we in the state 2? We were in the state 2, 4.3 minus 3.5, or 0.8, now times 2, which is 1.6. And so now our total area would be 1.6 plus the previous one, which is 3.0. Now here's the thing. So is that pretty clear how that would to you? Just because you're going to need to know how to do that. So now it's pretty clear when we're looking at this picture, but if we're running a simulation on the computer, we can't there isn't a picture, they're just the numbers. So the question is, how can we do that in a way which is algorithmic? In other words, if we can't do it in a mindless algorithm, then there's no hope of implementing it on the computer. And that's actually a general principle in my view. That is, if we need to think a lot to do any task, then there is no hope of implementing it on the computer. Okay, so how does this play out if we just have this bunch of numbers? Well, again, the idea is that at the very beginning, we're going to be, what I'm going to do is I'm going to look at the, I'm going to do a running average area under L. I'm just going to look at L, but okay. So we always start with 0 because at time 0, and we can kind of see this here, at time 0, the area is always going to be 0 because the width is 0. So we're always going to start at 0. And then, all right, so here's the first arrival event, and that occurs at time 2.1. And so we take the previous area, which is 0, and we add the previous state, which is 0, times the amount of time we spent in that state, which is 2.1 minus 0. And so now our running total is still 0. But now if we move to time 2.1, our previous value is now 1, but we've only been in there for a 0 amount of time. So it would be plus 1 times 2.1 minus 2.1. So again, 0. So it feels like we're spinning our wheels, but then all of a sudden, at time 3.5, our previous value of L was 1, so our incumbent was 0, plus 1 times 4.3 minus 3.5. And that gives us what is that? That's 0.8, et cetera. So, and if we do all that, well, okay, so yeah, so basically that's how the time averages go. Again, by now, hopefully you're convinced that the simple Talvi average is not correct in that it will not give an accurate depiction of what these averages were. And as you're saying, what we want is a weighted average. And what is it weighted by? It's weighted by the amount of time that you spend in each state. That's the weight. And that weight is exactly captured by the area under the curve. Now the thing is that because the discrete event simulation moves from event to event, because that's the only time that interesting things happen, then the idea is that we can compute the average up to that point, actually of both the tally and a time varying, if we have that, by, well, in the case of time varying, it's the previous state plus the current time minus the time of the last event. So now in terms that are kind of meant to bring flashbacks of calculus, technically, the area under the curve is the integral, so these are true regardless of whether our state trajectories are in fact discrete event ones or not. This is how you would find the time average of any type of thing. But fortunately for us, these are piecewise constant. Now, in this model, there are two tally averages that we would be interested in. And those are the average time in the queue, for each customer, and the average time in the system for each customer. Those are related ones. This would be the average number in the queue, and this would be the average number in the system, but this is the average time in the system. So in this particular case, if we have 100 customers and each one spends a certain amount of time in the queue, then our average would just be the mean of those. And likewise, if we were sitting there with each if each customer kind of knew when they joined the system and when they left, then that would be how long they were in the system. And so that's a tally average. Why? Because each customer is discrete. So if we have n customers, we have n of these observations, and so the way that we take the average is to simply add them up and divide by the number. Okay, so basically kind of continuing with the okay, yeah, so I think I had the wrong numbers on the previous one. Anyway, so yeah, but these I think are the correct ones. So this is how we would compute each of those values. So with the area under the curve for the number in the system, this is where we kind of made it to here. And it was 1.4 because at time 3.5 to 2.1, we had a value of 1 times that amount of time. Whereas here, we had an elapsed time of 0.8, but we were in a state of 2, and so we would add 1.6 to the area under the curve, and that would give us 3. Then here we went from 1 to 1 and 0 times, so that didn't add anything to it. And then finally, between the end service event at time 5.6 and the start service at 4.3, we add 1.3 to it, and that gives us the 4.3. And so the average number in the system when we finished at time 5.6 would be 4.3 over 5.6. And that was and then the other ones are done similarly, following exactly the same algorithm, but with slightly different numbers and slightly less interesting numbers. Now, in these models like this, where you have a server who's acting like this toward the customers, another measure which is often of interest is something called utilization. And utilization is basically how much the server was busy. And that's one of the things that you typically have to trade off a bit. So if you're managing this facility, I'm thinking in a commercial type of venture, on the one hand, you want your customers to be happy. And one way to make them happy, in addition to all the other things that you provide them, is that they don't have to spend a lot of time waiting in the queue, because nobody likes waiting in a queue. So the one way to guarantee that none of your customers will ever wait in the queue is to have one server per customer, so that when you show up, you always get service. Economically, that's usually not very viable. So queues are just kind of a fact of life. And so the other thing is that when you're when you hire these, like if I'm a bank and I'm hiring tellers, and I mean all they're doing is sort of sitting at their teller window, then I have to pay them per hour and not when they're I don't pay them. I say, well, you only spent 4 hours today serving customers, so I'm willing to pay you for 4 hours. Not how it works. So as a manager, you want the utilization to be high. But the trade-off is, in other words, you want them to be working. The higher the utilization, though, the higher the queues. So that's where the interesting trade-offs come that we won't entirely go into. But okay, how can we compute utilization in this context? So what we had was we had a state variable called S, which were the number of available servers. So that was kind of the opposite of what we really wanted. Utilization is typically computed on a per server basis. In other words, if we have K servers, then kind of unpacking this formula here, this is the area under the curve for the number of available servers. When we divide by T, that gives us the average number of available servers. When we divide that by K, that gives us the average number of available servers per server. And when we subtract that from 1, that gives us the average number of busy servers per server. And that's what utilization is defined as. So in this particular case, the average, or the area under the curve for the number of available servers turned out to be 2.1. The time that we finished was 5.6, that's T, and then in this case K was 1. And so that's where we get the utilization of 0.625. Okay, so that's, as you see, that we have to kind of apply some different formulas to do that. Now the other question that might come up is, well, what about the time? What about the average time that each customer spent either in the queue or in the system? Those are obviously related, but slightly different measures. Why? Because at least psychologically, when we're waiting online, the way we even perceive time and the way that we perceive our experience is going to be different than when we're actually getting service. So really, the amount of time we spend waiting online is the most obnoxious. And once we get service, at least we know we're kind of getting we're getting help. So, in other words, if I'm waiting at the Starbucks to get my latte, when I'm waiting online, they don't even know about me. They're not doing anything to get my latte to me. Once I get there, then okay, I'm waiting for them to finish the latte, but it's like they're working on it, and I know I'm going to get it shortly. Whereas when I'm waiting online, I have no idea when I'm going to get it. So what about the example for the amount of the average delay in the queue and the average time in the system? Okay, so here's the dilemma. Unlike the time-varying averages, we need the entire sequence of events for this model in order to do that. So we had 2 customers, and we need to kind of go back and say, well, okay, the first customer arrived at time 2.1 and left at time 4.3. And they started service at time 2.1. The second customer arrived at 3.5. They started service at 4.3, and then they left at 5.6. So, but notice, in order to do that, in order to get these numbers for this model, we need to go and we need to see the entire sequence of events like this. So in other words, our state variables, S and Q, don't give us out of the box what these values are. We have to kind of go through and pick them out of this. But that doesn't mean that they're not there. So first customer arrives at time 2.1. They start service at time 2.1, so their delay in the queue was 0. The second customer arrived at time 3.5, but they didn't start service until 4.3, so their time in the queue was 0.8. So how would you find the average delay in the queue for at least these two customers?
Time from individually from when each one arrived to when we started service, take that cumulative time and divide by the number of customers.
Yeah, so we have the first guy spent 0 in the queue, the second guy spent 0.8 in the queue, and so the average would be 0.8 over 2. So now for these, because these are tally means, we do it in the normal way. And for the time in the system, again, this guy, the first guy, showed up at time 2.1, but left at time 4.3, so their time in the system was 2.2. The second one arrived at 3.5, it left at time 5.6, and so their time in the system was 2.1. So their time in the system is 2.2 plus 2.1 divided by 2. Okay, so and as you can see, just with this little hand example, we can pull out the time averages, but we can also pull out the tally averages. So this is kind of how we would do this, but we would have to kind of look at the whole thing. That's the main disadvantage. But we can pull them out nevertheless if we're willing to do that. Okay, so here's the interesting thing. And this is something called Little's formula, which is a pretty kind of an interesting situation. This is something that people who have worked in these types of systems for quite some time, at least from an analytic perspective, have known about this for a long time. A fairly short time ago, just maybe a couple decades ago, there was a guy named Little who was writing a paper where he was using this, and this was common knowledge. Everybody knew this. And so he wanted to, being a good academic, since he was using this, he wanted to find the citation. So he combed through journals looking for where this had been published. And he found that nobody had ever published it, just everybody knew it. So he published it and got his name on it. Actually, he didn't put his name on it, but because his paper was the first published example of this, they gave his name. So so if you want to have your name on something, find something nobody else has done, but everybody knows, and write a paper about it. So that's okay. But it's a really cool result. Okay, we've seen two averages. We've seen the average number in the system, which is a time average. We've seen the average time in the system, which is a tally average. And there's kind of a third average, which is an arrival rate to the system. So if you were intuitively, if you hear the term arrival rate, does that you should have a pretty good intuition about that. The
Poisson distribution, is that what we're going to do?
No, not necessarily. Yeah, but that's yeah. You're. In other words, the Poisson process kind of plays a key role in the analysis of these types of things, but you don't need that. I mean, if let's say you wanted to know the arrival rate to the Starbucks, so what would you do? Yeah, exactly. You stand at the door, you'd sort of have like maybe a little clicker that would just sort of count them, and every time somebody came in, you would just sort of click it up by one, and then when you were finished, you would take that and divide by how much time you were doing it. So if I watched it for 2 hours, say, and I observed, 55 customers, then the arrival rate would be 55 over an hour.
You could just look up what the average arrival rate in Starbucks is and save yourself a lot of time.
You could. Do you think the arrival rate to the Starbucks on, where is it, in Seaside would be the same as the arrival rate here on campus?
It just depends on why we're trying to find it. If we're trying to actually make sort of commercial decision, I think we maybe would be accurate, but just giving us enough actual exercise and then just make that up and get some.
Yeah, you're right. It depends. So, I mean, if we're studying the Starbucks here on campus, the chances are the arrival rate is a little different than the ones that are kind of off campus, because the calling population is quite a bit smaller, because there are fewer of us here on campus than there are out in the wild. But yeah, very good point. If we're as a first cut, we would probably have access to this kind of data, and depending on the scope of the study. So if we were looking to, say, start a new one out there, then that would be the perfect place to start. On the other hand, if we were trying to analyze this one in here, and maybe they were saying, well, should we hire another barista to handle things, then you would want the arrival rate to this one. And probably the best way to do it would be that way. Or you could, what you could do is if they let you have access to their sales data, you could kind of look at that, just sort of count those up. But the point is, the average arrival rate is really just the either a historical one, which is done in the same way, which is just counting the number of things per unit time. But this is the astounding result. It's the when the system is empty, the average number in the system is exactly equal to the average arrival rate times the average time in the system. And that's one of these things that's either impossible or obvious, depending on how much you think about it. So here's the thing about how these systems work, especially ones that we, say, run on the computer. As you run it longer and longer, the system will either periodically empty out or it will blow up. Those are the only two possibilities. It will either sometimes empty out, in other words, have nobody in them, or it's going to blow up, meaning it's just going to, the number in the system is going to keep increasing forever. If your system doesn't blow up, then Little's formula, remember, it holds exactly when the system is empty, but it also holds approximately asymptotically as t gets larger. As you run your model longer and longer, it holds approximately. So how does that help us here? Well, in this particular case, you notice what we had to do in order to get these measures, which we are definitely interested in, the average time in the system and the average time in the queue. And we had to comb back through we had to keep sort of track of everybody, when they showed up, when they didn't, when they left, etc. But it turns out that using Little's formula, we can see that this actually, we could have skipped this and used Little's formula to compute both the average time in the system and the average delay in the queue. So in a simulation model, the arrival rate is going to be the number of arrivals over time. So in our example, we had 2 arrivals at time 5.6, and so our arrival rate was 2 over 5.6. Now, if you remember, our average number in the queue in the system was 4.3 over 5.6. Our average time in the system was 4.3 over 2, and our average arrival rate is 2 over 5.6. So if you look at this, the 2's cancel out, and we have exactly 4.3 over 5.6 on each side. Exactly, not approximately. And even now we can apply this to the queue itself, because we can look at the queue just as its own system. So the arrival rate to the queue was exactly the same as to the system. But in this particular case, the average number in the queue, we didn't explicitly compute it, but as we saw back here, it was 0.8 over 5.6. Oops. And so again, 0.8 over 5.6, the average time in the queue, average delay in the queue, was 0.8 over 2, and again, the 2's cancel out, and we get this exactly holding. Now, this would not be true if we looked at it when the system was not empty. It just doesn't hold. So if we were to look at this at time 5, for example, then at time 5, it would work for the queue at time 5 because the queue was empty, but it would not work for the system at time 5 because the queue was because the number in the system still had customers in it. What this means is that even though our basic in our model, it was relatively easy to compute the areas under the curve without having to remember all of the events that happened before. But to compute the delays in the queue and the time in the system, we had to kind of comb back through the whole sequence. And what Little's formula says is, well, you don't have to do that. If you run your system long enough, then it will approximately hold, or if you run your system until it empties out, then you can have those values exactly. Okay, so now here's another thing, just to kind of go back to our simulation by hand and say, what if we had the same exactly the same input parameters in terms of the arrival times, or the inter-arrival times and the service times, but what if we had 2 servers instead of 1? Well, that would be a different model. We would still apply exactly the same logic. Okay, so we would start with the time event and the states as undefined, and just a run event on the event list. You always start with that. Then you advance time to the next event, take the event off the event list. So here we'd go time is 0, run event. It initializes our state variables, and now the Q and L are 0, but the number of available servers is now 2 and not 1. And then run would schedule the first arrival at time 2.1, just as it did before. And then that's the end of that turn of the crank. Then we say, okay, is the event list empty? Nope. We move our time up to the time of the next event, take the event, perform its state transition. Its state transition of arrival is exactly the same as it was. We take Q and add 1 to it. So now Q is 1, S is 2, and L is 1. And then we schedule any events. So we schedule the next arrival at 3.5. That was exactly the same as before. And because S is bigger than 0, we schedule a start service at time 2.1 with 0 delay. And again, now, this is all the same as before, but it'll change in just a bit. So now at time 2.1, we move that, we take start service off the event list, we perform its state transition, Q goes from 1 to 0, S now goes from 2 to 1. This previous arrival was still there, and then our end service is still at 4.3. So up to here, it's exactly the same. But now things are going to be a little different, because at time 3.5, same as before, we got this arrival. Only now, S is bigger than 0. Because before, when we only had one server, S was 0 at this point. Now we have a server available. So because that server is available, we can schedule a start service event with 0 delay from here. So now you notice that now there are 3 events on the event list. So you might have the impression before that, okay, you're only allowed to have 2 events on the event list. Well, this disproves that. You can have as many events on the event list as you want. Okay, so we schedule our start service, then start service at 3.5. We schedule our end service now at 3.5 plus 2.3, I think it was, or 1.3. And so now we have 2 end service events on the event list. And then what happens is they're the next to occur. So we have the one at 4.3, and then the one, and then the final one. So in other words, for the same input data, we get a different state trajectory now. It was kind of the same at first, but then it deviated from the previous one, and now we would get different measures entirely. And I'll leave it, there's once we have this state trajectory, then, which is the time and the value, then we would compute the areas under those curves in exactly the same way. Okay, so now the next, what we're going to do next is we're going to kind of look at what we've done so far and see how it can be improved. The first is that our description of the multiple server queue model was had a lot of words on it. And it turns out that those words didn't kind of depict what was going on with these events. One of the key elements of these discrete event models are the relationship between the different events. Now, obviously, the events and the state transitions are of utmost importance, but the relationships between the different events are also key to understanding how this, just basically how the structure works. And that's where this event graph methodology comes in. And so in section 3 of the reading, this event graph methodology is introduced. And so for that, we're going to kind of go back to these 2 simple models, and we're going to redo them basically as, so that our arrival process is going to look something like this. And our multiple server queue model is going to look something like this, where we have circles and arrows, and the little nodes kind of point to each other. And so this is how our arrival process looks. This is how our multiple server queue model is going to look. And what are these circles? Those circles are the events. And what are the arrows? The arrows are just the scheduling relationships between them. So those are the things that we'll delve into that tomorrow. And that's actually what I have